Hello everyone, welcome back to the channel. In the previous video, we have discussed the concept of coupled models and also we have discussed the importance of coupled models for usage in hydrological purposes. So if you have not yet seen the video, you can find the link of the video in the description or you can find it in the I-bar here. So in the current video, we will discuss the concept which we can use for coupling of our models to get better results and predictions using machine learning models. So let's directly get into the concept which we are going to discuss in this video. The concept which we are going to discuss in this video is wavelets. So before we understand what wavelets is, we will try to understand what is the necessity of wavelets. So as everyone is aware that real world data is quite complex and it has lots of shifts and trends almost every year, and most of the time we are not sure about why these changes in shifts and trends are occurring. Hence, it is necessary to understand why these shifts and trends are occurring and why these changes are occurring. Understanding these shifts and change is the main goal because these changes and shifts give us valuable information about why these changes are occurring and what are the various effects of these changes. So, if we understand these changes, we can develop our models so that we can predict these changes whichever will happen in future. One technique which was used for understanding these changes in the recent past was Fourier transforms. Fourier transform is a kind of analysis. A sine wave with indefinite interval can be used for understanding the changes in the data to be able to see these changes and be able to predict them. Due to this advantage, this Fourier transform was mostly used in data analysis. This Fourier transform uses a constant signal which does not have any change in frequency to be able to understand this data. As you can see here in the first figure, you can see a constant signal where there is no frequency changes, whereas you can see the second signal which is a non-stationary signal which has lot of changes. So the Fourier transform uses the first kind of signal to understand the second kind of signal. The reason why non-stationary is being mentioned here is because most of the data in the nature is non-stationary as it has a lot of changes in its frequency along the time. So although this analysis was very good in the recent few decades ago, but due to the defect of not being able to understand a non-stationary signal, this has a liability in itself, thereby not giving good and accurate predictions for our data of importance. If we see in the right side here, this is the original value of a signal or any data set which is occurring in the nature, whereas the left is our sine wave which was formed for Fourier transform. So if we try to put one on top of each other and try to understand it, we can see that the changes in this data, as you can see in the figure here, are not being able to capture perfectly. Although there are slight similarities between the sine wave and the original signal, the overall changes are not being actually captured. So due to having this kind of disadvantage, the usage of Fourier transform diminished throughout decades and a new kind of analysis was developed to be able to understand the stationary data. One kind of analysis which has overtook Fourier transform is wavelet analysis. Wavelets are mathematical tools which are used for understanding a signal in both the domains of frequencies and time. Instead of usage of sinusoidal signals with indefinite interval as the Fourier transform use, here the sine waves are used with a definite interval, thereby trying to understand better compared to Fourier transform. There are wide range of wavelets available for use based on the kind of work being carried out or the kind of analysis or the variable of interest. So as you can see here, these are the different types of wavelets which are available for use. Some of the listed wavelets are Haar wavelet, Dauchis wavelet, Morlet wavelet, biorthogonal wavelet, Mexican hat wavelet, spline and Coupled wavelet. So based on the kind of analysis used and also the kind of data which we are dealing with, we can choose the different types of these wavelets to give us a better prediction. Having different type of wavelets for carrying out different type of functions is a major advantage of this wavelet analysis. So we have already talked about the different kinds of wavelets available, but we also need to understand what are the type of wavelet transforms which we can analyze. There are majorly two types of wavelet transforms which we can use. They are continuous wavelet transform and discrete wavelet transform. So let's first talk about what continuous wavelet transform is and also then discuss how it is different from the discrete wavelet transform. The major difference between the continuous wavelet transform and discrete wavelet transform is the difference between the type of scaling and shifting which is carried out in one another. Continuous wavelet transforms are mostly used for analytical purposes, where analysis is carried out for understanding the time frequency analysis of a dataset. This continuous wavelet transform is majorly used for understanding what are the time dependent components in the dataset and how they are influencing the overall dataset. The usage of this CWT for analytical purposes can be done using various kinds of wavelets. Some of the analytical wavelets we can use are Morse wavelet, bump wavelet, and analytical Morse wavelet. Using these wavelets, we can carry out the time frequency analysis and try to understand the variable of interest better. So using these wavelets, again there is a difference between the type of scaling which we carry out. As mentioned earlier, this is the major distinction between the continuous wavelet transform and discrete wavelet transform. As you can see here, the scaling factor, whatever we use, is inversely proportional to the frequency of that scale. Let's say we are doing a scaling factor of 2, then the frequency is reduced by the term of 2, thereby giving us different types of frequency values. Along with having this influence on frequency, another advantage which we have with continuous wavelet transform is it can be used for understanding the changes between two scales. Let's say we have a scale of 2 and 4. We can understand what is happening in between this octave by having various levels of scales in between 2 and 4, thereby giving us a better understanding of what is happening in between two scales. Based upon the scales, we also have the number of coefficients which are developed by doing this analysis, and these coefficients are the governing components in understanding how this wavelet transform is able to understand the data. So let's say we have 100 samples and we are using a scale of 20. The total number of coefficients which we will be getting are 2000. So using these coefficients, the CWT is trying to tell us how this data is performing and what are the various changes in the data, along with what are the time components which are influencing the data. So although this data set is giving us a lot of coefficients and is giving us more information, one biggest disadvantage is it has a lot of redundant information which can influence the outcome of the data, thereby sometimes giving us a redundant value. The next transform which we'll be discussing is a discrete wavelet transform. This is the transform which is majorly used earlier for denoising or compression of a signal. As you can see in the figure here, the picture in the first image has a lot of noise, whereas after we use DWT, the picture in the right shows that a lot of noise components are removed. So this is how denoising is done for a picture. Whereas when we come to compression of a signal, as you can see here, the signal is having a lot of ups and downs which are considered noise due to sudden changes in the data set. So in order to understand how the data is varying, we have to remove the noise, and this DWT can be used for this removal of noise and thereby provide us valuable information about how this data is varying. Another advantage of this DWT is it has an ability to represent the natural components well. That is, it is able to represent the natural signals better compared to the CWT transform. Another big advantage is it does not have any redundant variables, thereby reducing the amount of issues caused in the analysis, and also it takes up less memory, thereby giving us a better result far quicker. When we think about scaling difference between CWT and DWT, we can see here that the scaling factors used in the DWT are to the base of 2 to the power of I. As you can see here, I represents the number of integers which we can use. So using this base component of 2, varying different scales are developed for analysis of different data sets. So this is the basic understanding about what a CWT transform is and what a DWT transform is. So both of these transform have their own advantages and disadvantages, although the type of analysis you want to do determines what are the kind of transforms which we can use and what are the kind of wavelets which we use for our analysis. So in our next video, we will discuss about how we can use these transforms to understand the changes in the data based upon few examples which you'll be seeing using various data sets like precipitation and its relation to a discharge component. So that is it for this video. If you have any questions regarding wavelets, you can put the questions in the comments and I will answer them as soon as possible.